So, returning to our series on kinematics. Before us in the graph, we have an object moving and displacing as we move through time. We have previously looked at linear motion, but now we will consider motion that is non-linear, essentially an object that has a variable velocity and acceleration. This is illustrated by the fact that we have a curve and not a straight line. Now, consider the graph where an object has motion of d equals 2t cubed minus 6t. We have marked the points on the lines of 1 minus 4 and 2 positive 4. This means that after 1 second the object has moved 4 meters in the negative direction, and after 2 seconds the object has moved 4 meters in the positive direction. So our object has changed the direction that it is moving. Now, what if we wanted to calculate our velocity at any point on the graph? Unlike our previous examples that had linear motion, we cannot use the formula for the steepness of the line as the difference of the distance travelled divided by the difference in the time. So we cannot use v equals d2 minus d1 all over t2 minus t1. We cannot use this. So what do? Well, we use differentiation. I'm assuming that you are familiar with differentiating basic expressions, but all it is dropping the power by 1 and multiplying the expression by that power. That is v equals n a t n minus 1. So applying this, we get v equals 3 times 2 t 3 minus 1 minus 1 times 6 t 1 minus 1, which gives us 6t squared minus 6. And this is our equation for the velocity of the object. So we have just differentiated our equation for the distance covered by the moving object that has given us the velocity. We found that the differential v, or dd over dt, equals 6t squared minus 6. We now have the graph for the velocity in time, and we can observe its behaviour. As before, we have marked the 2 points on the graph at t equals 1 second and t equals 2 seconds respectively. We see that the velocity at the start is minus 6 meters per second at the origin. So at the origin 0, when time t equals 0, we have minus 6 meters per second. It then comes to a stop at t equals 1 second, so the velocity is 0 here, 0 meters per second. The object then moves in the positive direction, and at 2 seconds the velocity is at 18 meters per second. So 18 meters per second. The velocity then increases exponentially for the remaining time. Now, what if we wanted to find the acceleration of the object at any point? Well, again, we would use differentiation. So as before, let us differentiate the equation. So a equals dv over dt equals 2 times 6 times t2 minus 1. The constant minus 6 just becomes 0, so that's minus 0. So the acceleration equals 12t. And this is our equation for the acceleration of the object. So we have our equation for the velocity. What if we wanted to find the distance travelled? Well, again, we'd use integration. So the distance travelled would be nothing but d equals the integral of 6t squared minus 6, which equals 6 t cubed over 3 minus 6t plus our constant of integration. So cleaning this up, we'd have equals 2t cubed minus 6t plus c. Now we know that the distance at time equals 0 is 0. So we just plug that into the equation. So 0 equals 2 times 0 cubed minus 6 times 0 plus c, and this is nothing but 0 equals c. So our final integrated equation for the distance is just d equals 2t cubed minus 6t. If we go back to the beginning, we see that's exactly what we had here. So there we have it. Now we have our equation for the acceleration of the object, and we can now look at its corresponding graph. Again, we have marked the points at 1 second and 2 seconds. We see that the acceleration is increasing at a constant rate. At 1 second, the acceleration is 12 meters per second squared, and at 2 seconds it is 24 meters per second squared. Because of such a steep curve, the velocity will become excessive and so cannot go on for much longer. Now we have gone through 2 steps of differentiation, from distance to velocity and from velocity to acceleration. But what if we were given an example where we started with acceleration? Well, we would do the inverse of differentiation, which is nothing but integration. So we would integrate a equals 12t with respect to t. However, there's one important parameter that we need. We need to know the velocity at some point for when we add on our constant of integration. So let's say we know that the velocity at 1 second equals 0. We would perform the following steps. So we would have v equals the integral of 12t with respect to t, which equals 12t squared over 2 plus the constant of integration c, which equals 6t squared plus c. So if the velocity is 0 at t equals 1, we would simply equate the equation to 0. So 0 equals 6t squared plus c. So if t equals 1 at v equals 0, we would have 0 equals 6 times 1 squared plus c, which would be 0 equals 6 plus c, which would mean that minus 6 equals c. So our finally integrated equation is v equals 6t squared minus 6, which is the same as what we did up here for our velocity, the equation of our velocity. So there we have it.